You can see my shared screen.
Yes.
So again, apologize for the delay. Zoom all of a sudden wanted to update and it wouldn't let me update in our normal classroom. So I had to sort of switch to my laptop. I wanted to just kind of summarize some things and then prove those two theorems that I mentioned at the end of Monday. So we'll do that work on the board here in just a second. But we were talking about eigenvalues and eigenvectors of an operator. And in particular, we're interested in Hermitian operators, which we're going to find out why we're so obsessed with Hermitian operators today and prove that they have real eigenvalues. But this is just a summary of a bunch of ideas, some of which we've touched. There's a couple of things in here that I wanted to still mention today. Okay, so what is the meaning of eigenvector and eigenvalue? We talked about this way back when. If I have an operator and I say that operator operating on some state gives just a number times that same state back again. In other words, this state is a special state that's sort of left with its direction unchanged. It just gets rescaled by a number q, but its direction doesn't get changed. That's a very special state. That state is called an eigenvector, and that corresponding value that appears there is called the corresponding eigenvalue to that eigenvector. We mentioned last time that one of the reasons we're concerned about eigenvalue equations is that for Hermitian operators, when you find the eigenvectors, they are determinate states for that operator. That means the corresponding dynamical quantity could be momentum, could be total energy, could be position, is a state for that variable that has zero uncertainty or zero standard deviation for the probability density for that variable. Okay, so for example, if we take the operator, the momentum operator, and we solve momentum operator times a function of x equals a number times that same function of x back again, that's a differential equation. We can solve the differential equation, and we will find states which have a definite value of momentum. Their momentum is zero everywhere except at a particular value. So that's what a definite determinate state means. Here's the thing I wanted to mention that I didn't mention last time. When you're talking about a linear operator, and all of our operators in quantum mechanics are linear, the zero vector always satisfies the eigenvalue equation, because any linear operator operating on zero gives zero back again. And so in some sense, it's a trivial solution to the eigenvalue equation, but we're never going to consider it an eigenvector. So even though the zero vector technically satisfies the eigenvector equation, we don't consider it an eigenvector because it's not a normalizable state. So no normalizable states are going to be, no non-normalizable states will be considered. Now, here's a point of confusion. Zero itself, the number zero, can be an eigenvalue that appears in this location here, right? The vector itself can't be the zero vector, but zero can be an eigenvalue as long as it corresponds to a non-zero eigenvector. We'll see that happening later on, okay? But the zero vector can't be an eigenvector, and we're going to use that property soon. And we talked about the collection of all eigenvalues of a particular operator that either lie in our original vector space of square integrable functions, or we said we're going to slightly, put it on steroids where there's a few extra functions that don't diverge really dramatically as you go off to infinity, but they might oscillate as you go off to infinity, and they still have finite inner products with good old-fashioned square integrable functions. That enlargement of that space is called the rigged vector space, or the rigged extension to square integrable functions. Okay, the collection of all eigenvalues of that is called the spectrum of that particular operator. So we've seen the spectrum of the total energy operator. Spectrum of the Hamiltonian is something we've thought a lot about. And then finally, sometimes you'll find that corresponding to a particular eigenvalue, there's more than one linearly independent eigenvector. And that's a case where we would say the spectrum is degenerate, or that's a degenerate eigenvalue if there's more than one linearly independent eigenvector corresponding to it. And that would be kind of like the case where we said for each energy for the free particle, there were two states that corresponded to it, right? There's an e to the ikx kind of state and an e to the minus ikx state. They have opposite momenta, but they have the same energy. So, all right. Now on to our theorems that, what the whole point of talking about Hermitian operators is so that we can use that property, the definition of Hermitian, here to prove these two theorems. And we're going to do those on the board just to kind of slow it down a little bit. The proofs are in the notes that you have, but you may want to annotate the notes. So let's just write it out completely and carefully. Let me pin my video here and try to get this so I can get a decent amount of the board here. So our first proof is going to be of the theorem that the eigenvalues of a Hermitian operator are real. And you should know this proof. So write it down, think about the steps. One of the steps doesn't make rigorous sense. We can talk about refining how to make that step further. Okay, so our theorem eigenvalues of a Hermitian operator are real. And here is the proof down here. So in order to use the proof, we need to kind of write down, if we're talking about eigenvalues, there's some eigenvalues and there's a corresponding eigenvector. So let's let f, this vector f, be an eigenvector of some Hermitian operator, okay? We're assuming this is Hermitian. Okay, it satisfies that weird definition, okay? What that means is that Q operating on F equals some little q times the same F back again. So this is an eigenvector. We're going to call the corresponding eigenvalue Q again, okay? Now, if Q is Hermitian, we're assuming Q is Hermitian here. So since Q hat is Hermitian, what that means is in an inner product, I can willy-nilly move the operator from one side of the inner product to the other. Okay, so it certainly is true that if I have Q operating on F, inner product with F, normally, if I weren't talking about a Hermitian operator, I'd have to put a dagger on this over here on this side. But since we're assuming Q is Hermitian, we don't need that dagger on it, okay? So since Q is Hermitian, those are equal. And now let's just start working on this side. So I'm gonna have some equalities going down here, some equalities going down here, and then we're gonna set those two things we end up with equal there, okay? Again, when I have a vector, this vector that's drawn right here, when I write down the vector with the label Q hat F, that's just supposed to remind me that it means it's the result of Q operating on F. So another way to sort of expand this out is to say, we want to take the inner product with F of the result of Q operating on F That's just notation. That's what we mean by this notation for a vector. It reminds us that it's what happened, or it's the vector we got after that. And this, of course, right here, by our assumption of the eigenvalue equation, right? F is supposed to be an eigenvector of Q corresponding to eigenvalue Q. Okay, so the thing on the right-hand side is little q operating on F. And if I have a multiple of a vector inside an inner product, I can always factor it out of the inner product. If you like, you can think of the definition of the inner product in terms of an integral of a product of functions, one of them star, right? If you've got a number like 3 sitting inside that integral, you're welcome to factor it outside of the integral. So I'm going to rewrite this as q times the inner product of F with itself. Okay, maybe F is normalized, maybe it's not. We don't really care right now. That's the left-hand side. Okay, let's do a similar thing for the right-hand side. We're first going to use one of our inner product axioms, and maybe I'll just flash that up for a second. I'll remind you of our axioms for an inner product. Let me arrow forward here. So these are our axioms that every inner product has to satisfy. We're going to use conjugate symmetry right now, but I want to point out, because we're going to use it in just a second too, the important properties we're going to use is whenever I have an inner product in one order, I can always flip it around as long as I put a star on the whole mess, right? Complex conjugate. We're also going to use the fact that the inner product of a state with itself is a real number. It's a non-negative real number. When we say it's greater than or equal to 0, that's never a complex number. That means a real and also non-negative number. And it's equal to 0 only if the vector itself is the 0 vector. Remember, that means that if the length of a vector is 0, it's got to be the 0 vector. There are no other vectors that have length 0, because the length is just the square root of the inner product of a state with itself. Okay, but right now I'm going to use conjugate symmetry right here. Okay, so what I'm going to do is flip it around. This is the same thing as F inner product with QF, as long as I put a big star on the whole mess. That's conjugate symmetry. All of our inner products satisfy that. Okay, now I'm going to do the same trick I did before. I've got this QF there. I'm going to skip the middle step, but we could write this as, let's keep the star on the outside. This is little q multiplying F, and that little q can be factored out in front of the whole mess. Okay, so this ends up being kind of the same thing that's over there. Q times the inner product of F with itself. Okay, all of that's under the star. And now we're going to use, for a last bit of simplification, when you have the complex conjugate of a product of things, you just take the complex conjugates of each one in there. Let's take Q star, and I don't need to put a star on the inner product of F with itself. Why is that? It's going to be real. Remember, the inner product of any vector with itself is always real and non-negative. So here we're using the fact that it is real. Okay. Remember, that represents the square of the length of the vector. So we want to be able to take the square root of it, and it's always going to be non-negative. Okay, I've got my string of equalities now. I'm going to set this equal to this. And let's put everything on one side and set it equal to 0. So when I set this left-hand side equal to this right-hand side, we end up getting, let's see, can we see over here? Let's move a little bit in this direction. We get Q minus Q star multiplying the inner F itself equals 0. I've set these two equal to each other and just put everything on one side, factors out the inner product of F with itself, and all that's left is 0 on the other side. And now I'm going to use your old favorite algebraic technique from high school or junior high or whenever you learned it, if the product of two things equals 0, either one of them has to be 0 or the other one equals 0. So either Q is equal to Q, or Q star is equal to Q. That would be saying that the eigenvalue is real. Or the inner product of F with itself is 0. So we have to chase down this other possibility a little bit more. What if the inner product of F with itself is 0? What would that imply about F? Right. This means that F is the 0 vector. Now, why does that violate our assumption back at the beginning? Right. We're assuming F is an eigenvector, but 0 is never an eigenvector. So this cannot be true by our assumption. And therefore, this is true. And so the final conclusion is that Q is real. The eigenvalues of a Hermitian operator are real. Okay. Now, well, okay, any questions about this proof here? You might have to write it down a few times, but on our exam next week, this is something that you might be asked to just say out, right? Because it's sort of simple and sweet, but it's easy to get lost in there. So if you haven't, you need to know, where do I start? Okay, use the Hermitian property. I've got to define the eigenvalue equation and write this down, and then try to simplify everything down until I get an F, inner product F at the bottom, and chase out the conclusion there. Okay, questions on that? All right. Let's go on to the next theorem, which is that the eigenvectors of a Hermitian operator corresponding to distinct eigenvalues are orthogonal. And this proof, once we've proven that the eigenvalues are real, is actually a little bit simpler to do. We don't have to use quite so many properties of the inner product. Eigenvectors of a Hermitian operator, again, we'll call it Q, corresponding to distinct eigenvalues are orthogonal. Okay, we've seen this before, for example, in our work back in chapter 2, where we were finding energy eigenvectors and eigenvalues quite a bit, although we didn't always use that language back then. And we would say, if we're talking about the harmonic oscillator potential, the total energy values that are eigenvectors of the total energy operator are n plus 1/2 h bar omega, and the corresponding eigenvectors are those psi n's that were the Hermite polynomials times the Gaussian functions. And we verified back then, at least for the first couple of cases, that if you took the inner product of psi 1 with psi 2, you did that in the homework, and you found out it was 0, right? And the inner product of psi 1 with psi 3 was also 0. I think those were the homework. So here we're going to show that this is true in general. Okay, so we're going to start out in a similar way. Let's define, here we have to talk about two different eigenvectors and show that they're going to be orthogonal to each other. So let's let F and G be eigenvectors of Q. F and G be eigenvectors of Q with distinct eigenvalues. Okay, so what that means is we're going to assume that Q acting on F is equal to some number Q times F back again, and Q operating on G is some other number Q prime multiplying G again. And we're going to assume that Q is not equal to Q prime. In other words, we're interested in investigating what happens when there are distinct eigenvalues. If they're the same, of course, we're taking the inner product of a function with itself, and then, or we may be, and in that case, it's probably not going to be orthogonal. Okay, so again, let's start with the assumption that it's Hermitian and use that. This definition of Hermitian is absolutely crucial for this. The assumption that it's Hermitian, in this case, I'm not going to put the same vector F there, but I'm going to use the two different vectors F and G in an inner product, right? The assumption that it's Hermitian means that I can put this Q over here without changing it at all in the inner product. I don't need to put a dagger on it. And again, we're going to work on both the left-hand side and the right-hand side. The left-hand side is easy. We said Q, so this is just notation for the result of Q acting on G. That's Q prime acting on G, and that Q prime can be factored out in front of this. So after maybe 2 steps of work there, I would get Q prime times the inner product of F with G. Okay. On the right-hand side, I'm going to do the same trick as before. Let's first flip it around and put a star on it. This is the complex conjugate of G inner product with QF. Q operating on F gives, by assumption, little q times F back again, and that little q can be factored out in front. Q times the inner product of G with F. All of that is starred, complex conjugate, right? And then the complex conjugate of the product is the same thing as the product of the complex conjugate. So this is going to be equal to Q star times, well, the inner product of G with F starred is the inner product of F with G. That's that conjugate symmetry. When we flip it around, we just put a star on it. Okay, questions so far down there? Now we're going to use our previous proof, which is that we already showed that the eigenvalues of a Hermitian operator are real. So I don't really need this star down here. So the justification is that Q is real based on our previous proof. Okay. And again, we're going to set this equal to this, put everything on one side, and that says that therefore Q prime minus Q times the inner product of F with G is 0. And either the first one is 0, either Q prime is equal to Q, that would be what makes this 0, or the inner product of F with G is equal to 0. And this is not true because we already assumed that the eigenvalues are distinct. Q is not equal to Q prime. So this can't be true by our assumption that the eigenvalues are distinct. And therefore, in this case, the conclusion is that the two states are orthogonal to each other. Okay, so that means that eigenvalues, eigenvectors corresponding to distinct eigenvalues are orthogonal if you're talking about eigenvectors of a Hermitian operator. So these two key properties, the reality makes it correspond to a physical observable, right? We don't want to measure a physical observable and find a complex value. And also, one of the key results that we saw happening over and over again back in chapter 2 is sort of generally true for Hermitian operators. The Hamiltonian is just one of many examples of Hermitian operators. Okay, and again, any questions on those two kind of short proofs? Yeah.
Can we get eigenvectors with the same
We can, yes. We didn't see it with the, and there's a theorem you can prove that if you have a Hermitian operator with a discrete spectrum, then if you're in one dimension, in other words, we're just talking about functions of x, not functions of x, y, and z. We'll go into 3 dimensions later on. But in one dimension, every operator with a discrete spectrum, wait, I'm forgetting what your question was. That it.
Can we get the eigenvector with the same?
Yes. So the spectrum corresponding to discrete spectrum in one dimension is always non-degenerate cases. In other words, for every one eigenvalue, there's only one corresponding eigenvector. Linearly independent. I mean, you can always multiply it by a constant, but there's not another linearly independent one. But we'll see this happen all the time in 3 dimensions where we get degeneracy. And if we've already seen that even in 1 dimension, if you have a continuous spectrum, you can get degeneracy. But in the case where an operator has a discrete spectrum, for every eigenvalue, there's always only one corresponding eigenvector in 1-dimensional quantum mechanics. All right, let's go back to the slides now. Let's see where we are here. Okay, so we've just proved these 2 important properties, and we're about to add one onto it, okay? Hermitian operator with a discrete spectrum. Well, I didn't really mention a discrete spectrum there, but the problem that goes wrong if you don't have a discrete spectrum is whenever you have a discrete spectrum, that's when your eigenvectors are going to lie in the set of square integrable functions, okay? And that's the case where the inner product is going to be well defined, okay? So we're sort of implicitly assuming the discrete spectrum case here by assuming that these inner products even make sense. Now, if you're talking about eigenvectors that are not, that are part of a continuous spectrum, they're going to be like those e to the ikx functions that might not be normalizable. And so f, inner product f, isn't going to make any sense. And the inner product between 2 states might not make sense. And so this proof is really questionable in the case of continuous spectrum. But at least for the discrete spectrum, all of the corresponding eigenvectors lie in the space of square integrable functions, like we saw for, say, simple harmonic oscillator potential, or for the infinite square well. Those were pure discrete cases. All right. Now, Yi-Chen's question is important because it's going to come up in 3 dimensions. What happens if there is degeneracy? What if we have more than one eigenvector that corresponds to one eigenvalue? Well, that means that we're not necessarily guaranteed that the 2 states are orthogonal to each other. Oops, that was a mistake. But we now know a process, and this will always work. If you do have degeneracy, the states that are degenerate might not be orthogonal to each other. But you can always make them orthogonal and then normalize them. And I can normalize any state that I have so that I end up getting an orthonormal set. So it's, if I have a Hermitian operator and I find all of its eigenvectors and it corresponds to a discrete spectrum, some of the eigenvectors might be degenerate states and they might not be orthogonal to each other. So the proof doesn't apply there. But I can always out of that set, if there are 3 degenerate eigenvectors corresponding to 1 eigenvalue, I can use the Gram-Schmidt method to form out of them, by mixing them up in a certain way, an orthonormal set. And so we're going to assume from now on that our eigenvectors in the case of a discrete spectrum can be made into an orthonormal set. You can always normalize them. They're going to lie in capital L2. And if they're not orthogonal to each other, you can form them by form an orthogonal set by using the Gram-Schmidt method. It's a lot of work, but it's important that it can be done. Okay, so those are 2 important properties, and we're going to contrast them with the continuous spectrum case coming up. But here's a third important property that we would like to know about: the completeness of the eigenvectors. Remember, we want to be able to write any function, any vector, as a linear combination of eigenvectors, like we did with the total energy operator, the Hamiltonian. So let's write that down. Okay. You know, I would like to be able to say, here's an arbitrary square integrable state. Maybe it corresponds to my psi at time t equals 0. I'd really like to be able to write that as a linear combination of, I guess in this notation, I should write this as an abstract vector, psi n. Or equivalently, you know, the way we used to write it is we would say some arbitrary function of x can be written as some linear combination of the psi n of x's. That assumption that we can do that is based on the fact that the assumption that this selection or this collection of functions is a complete set, or a complete set of vectors. If not, you know, I might be able to come up with a function where even if I use all of these and I choose creatively what the CNs are, it's not possible to do that. So we're concerned with completeness. Now you're going to find out that I'm following Griffiths here, and it sounds like a little bit of a cheat, and it sort of is a little bit of a cheat, because the assumption of an operator being Hermitian apparently isn't enough. There are no Hermitian operators that we're going to run into in quantum mechanics that don't have a complete set of eigenvalues in the case where the spectrum is, eigenvectors in the case where the spectrum is discrete. But there are ones that you can make up. So if you're a mathematician, you worry about this kind of stuff. And you can come up with examples of operators that are Hermitian operators, but they don't have a complete set of eigenvectors. And so Griffith says something to this effect. We're going to define the definition of an operator corresponding to a physical observable is not just a Hermitian operator, but a Hermitian operator with a complete set of eigenvectors for square integrable functions. He's sort of defining his way out of it, saying, you know, we're not going to call it a physical observable, an operator corresponding to a physical observable, unless it's both Hermitian and has a complete set. I'm not going to say anything more about it because I don't know any way to get it beyond this. You know, I'm sure someone who's an expert in functional analysis could probably say something more deep than this, but this is probably the limit of Griffith's knowledge of the state of things too. Okay. Finally, one more comment, and that is, at least for the case, again, here we're just talking about the discrete spectrum. All this stuff about inner products and norms and all that doesn't make sense in the case where you have a continuous spectrum, because that's the case where your functions are not normalizable. For an operator with a discrete spectrum, the eigenvectors will always lie in capital L2. That means they will be square integrable functions. And that agrees with everything we've seen back in chapter 2 as well for the Hamiltonian, right? For both the infinite square well and the harmonic oscillator, the eigenvectors were square integrable functions, right? They were either the sine function that went to 0, so that made it square integrable, or the Gaussian function times the Hermite polynomials, which are square integrable. Okay, so to summarize, I know this, all the stuff we're talking about is sort of overwhelming, but this is a big sort of summary of what we've learned so far, at least corresponding to the discrete spectrum case. A Hermitian operator representing an observable with a discrete spectrum. Okay, so an observable corresponds to an operator, and we're going to assume for right now the operator has a discrete spectrum. Things are a little bit more complicated in the continuous spectrum case. We showed that it has real eigenvalues. It has a collection of eigenvectors that sort of by definition is complete, because that's what we mean by an observable, an operator corresponding to an observable. And even if they're mostly orthogonal, and so they can be normalized, and they can be made into an orthonormal set. And therefore, the collection of eigenvectors of any observable operator forms an orthonormal basis for the set of square integrable functions. And so we can write things like this kind of without thinking and solve for the coefficients by the method we used to do. Okay, so we're not introducing a whole lot of new machinery in terms of how we're going to work in quantum mechanics, but reassuring ourselves that the kind of really interesting properties we saw back in chapter 2 weren't just flukes for those cases. They're going to happen in general, at least for the discrete spectrum case. All right. Now, the natural question is, well, what about continuous spectra operators? Or what about combined spectra? We saw some that are combined, right? The Dirac delta function potential had one bound state, which you could think of as a discrete part, and then a continuum of scattering states. The finite well had a finite number of bound states that were discrete, and then a continuum of scattering states. So those are cases that really we still have yet to talk about. They're either continuous or combined continuous discrete spectrum cases. And I'm going to follow Griffith's discussion that you saw in the reading. I know the reading was quite a few days ago when you did this, and I'm trying to elaborate a little bit more on what Griffith says here. The proofs of properties 1 and 2, that's the realness and the orthogonality properties that we proved, fail since the inner product isn't defined outside of the Hilbert space, the set of square integrable functions. You take the inner product between functions that aren't square integrable, you're not necessarily going to get some sensible value. So it's only defined on capital L2. And in general, without some more clarifying remarks, properties 1, 2, and 3, 3 was the completeness statement that was almost by definition. These don't have to be true in the case of a continuous spectrum, but if we think about it, we can kind of make analogous things hold in the continuous case in the context of a rigged Hilbert space, adding in those extra functions on top of capital L2. Okay, so this is the example, I believe, if I remember correctly, that Griffith sort of follows through. In order to get an idea of how to go, let's try to find the eigenvalues and eigenvectors of the momentum operator. Let's write down its eigenvalue equation. That's going to be a differential equation. We'll try to solve it. And then we'll think about, are the eigenvalues going to be real or could they be complex? Are different eigenvectors orthogonal or not? Okay, so here's what happens. Here is the eigenvalue equation for the momentum operator. Momentum operator operating on some function, and I'm putting a subscript p on there because it's going to correspond to eigenvalue p times fp of x. So this is saying the operator multiplying on this function gives a constant times that same function back again. And that's a differential equation that's really easy to solve, right? That would be week 1 in your differential equations class where it's a separable differential equation. So the solutions are these complex exponential functions. Without thinking about it too much, just write down what the solutions are by writing df over f and integrating both sides and the stuff that you did long ago. And at least on the face of it, you might ask yourself, well, what values of p are allowed here? And at the beginning, we might say, well, any complex number, that's supposed to be one of those bold-faced C's, right? The set of all complex numbers. That momentum number might be any complex number. Suppose if it's a real number, then we get an oscillating function here. What kind of function will we get if P were pure imaginary? Suppose, I'm saying in SI units, P could be I. If P were I, then how would this function behave? Yeah, it would be an exponentially decaying to the right kind of function or increasing to the left. Now, that is not a normalizable function, but we're outside the land of normalizable functions. This is not a normalizable function either. So there's no reason to dismiss that out of hand right away, right? I mean, they're sort of both not normalizable. Why should we throw away an exponential function, at least at the beginning, if we're going to keep oscillating functions like this? In general, if you have a complex number that you put in for P, it's partly oscillating and partly, but its amplitude is either increasing exponentially or decreasing exponentially. So it blows up to one side or the other. So it's not normalizable either. Okay, so at least at the beginning, we're going to keep those. So these are provisional eigenvectors and eigenvalues. And now let's think about, well, wait a minute. An eigenvector has to lie in the vector space. And so are these really eigenvectors? And are these really all the corresponding eigenvalues? And Griffiths gives two takes on this. One he calls the strict interpretation. And the strict interpretation is saying, forget about the rigged Hilbert space. Our vector space is capital L2. Everything that we're talking about has to be a square integrable function. And none of these, doesn't matter what complex P you take, are going to be square integrable. They're either blowing up to one side or the other, or they're oscillating forever. None of them are square integrable. So the things we're calling eigenfunctions, in scare quotes here, that we found are not in capital L2. And I can't remember, I may be switching between different people's notation, but I should have put that as a superscript. That's the way I've been writing it before this in class, but at some points I switch to the other. If they're not in our Hilbert space, and we consider our Hilbert space to be capital L2, square integrable functions at all, then these aren't eigenfunctions. And so we could say the spectrum of the momentum operator is the empty set, because we couldn't find a single eigenvector. And so there are no corresponding eigenvalues, right? And so there's nothing to discuss with properties 1 through 3. Are the eigenvalues real? Well, there aren't any eigenvalues. Who cares? Are they orthogonal when they have different eigenvalues? There aren't any eigenvectors, so there's nothing to talk about. Are they complete? Well, no, they're obviously not complete. There aren't any of them, so there's really not much to say here. And in a lot of quantum mechanics textbooks, you will find, this is not true in Griffiths, but in older quantum mechanics textbooks, there is sort of a tendency to really backpedal to this when really pushed on anything. Hey, empty spectrum. There's nothing to talk about. We don't have any eigenvectors, the momentum operator. That would be to say, if you ask someone, are there any definite momentum states? They would say, no, not for a single particle. Single particle can't be in a definite momentum state, because by definition, it wouldn't be normalizable, and therefore there's no sense to the probability, and we don't even know what we're talking about. We want cases that have an easy interpretation for their probability. Okay, so that's the strict interpretation. Now, the whole point of all this stuff about rigged Hilbert spaces is that Griffiths is going to say, well, let's take a more modern or liberal interpretation of what we're seeing up here. And again, let's rethink it. I found some provisional eigenvectors and eigenvalues. Let's think about them in the context of a rigged Hilbert space. First of all, the functions we found, we already found out they're very useful. They correspond to scattering states. They correspond to beams of particles. And maybe I can't make sense of a beam in terms of a single particle, but it makes sense to put a whole bunch of particles, infinite collection of particles in a beam that has a definite momentum or a definite energy. So they're certainly useful. We shouldn't just throw them away out of hand. And we found they lie in a slightly larger space than this. In other words, the rigged sort of expansion of capital L2. So we have some motivation to try to make it work. Now, we've observed by thinking about what happens if P becomes complex. If P has any imaginary value part to it at all. In other words, if P is not real, maybe it's worth drawing this on the board. If P is not real, we're talking about functions that are like this, e to the I px over h bar. If P is real, then this is oscillatory, right? P is real. We get the behavior looks kind of like this, our old friend, the oscillating complex exponential function. If P is purely imaginary, that means a multiple of I, then it's either blowing up to the right or it's blowing up to the left. It's an exponential function. If P is a more general complex number that has both real, non-zero, real, and imaginary values, as I said, it's sort of oscillating, but the amplitude's getting bigger and bigger exponentially as you either go to the right or go to the left. All right. So let's continue that thought. So if P is real, they just oscillate, okay? And in that case, the inner product of one of these functions with a perfectly square integrable function, like I wouldn't be able to interpret it in any easy way, the inner product of this function with another one of this type, because I get a divergent integral. But if I take the inner product of one of these functions with a perfectly square integrable function, an element of capital L2, then it will be defined, because my square integrable function has to go off to 0. And so I don't get an integral that I keep adding up area farther and farther out. Okay. So we're going to expand our vector space slightly in this liberal interpretation and say, well, I don't want to just stick to capital L2. I'm going to take the rigged expansion of capital L2 and add in those oscillatory functions that have finite inner products with square integrable functions. But we're not going to allow this kind of genuine exponential blowing up. And we're not going to allow the amplitude of an oscillatory function to blow up exponentially either. Because if you take the inner product of any one of these kinds of functions with a square integrable function, it might not have a well-defined norm or inner product. Sorry, I'm talking about an inner product there. And that's because, I might have defined a square integrable state that is I might say, here's a perfectly good element of capital L2. E to the minus absolute value of x. That goes up like this, and then out like that. It's perfectly square integrable, right? There's a finite area under the square of that function when I square it. Now, if I multiply it by a growing exponential, the growing exponential sort of cancels out the decaying exponential part of this, and I get an area under the curve for an inner product that just keeps going and going and going. So those inner products wouldn't necessarily be defined in that case. Okay. And therefore, we're motivated to say, well, I don't want to take all eigenvalues. I want to restrict the ones I'm going to call eigenvalues to those that are real, and that will restrict the corresponding eigenvectors to just the ones that are in our rigged Hilbert space, the ones where we've taken square integrable functions, but we've added on these extra functions, which are either oscillatory, or technically when we added them on, we mentioned delta functions too, right? So we're going to say, add on to capital L2 functions that aren't square integrable, but still have a finite inner product with those. And we're also going to add in delta functions, which technically aren't even functions at all, right? So when we're thinking of functions, we're thinking of things that have finite outputs. A delta function is technically not a function at all, despite the name. Okay. And therefore, if we take this definition, the eigenvalues of Hermitian operators in the continuous spectrum case will again be real, or at least it works for the momentum operator, okay? And it will work for the other operators too. Why are they real? Because if I took any complex part of it, I'm going to get something that is blowing up in one direction or the other so badly that it wouldn't have that finite inner product property with other elements of just good old-fashioned L2. Okay, and in that case, okay, the eigenfunctions are going to lie in the rigged Hilbert space. They're not going to lie in the original Hilbert space, but they will be a complete set still for any square integrable function. So what I want to be true is that if you give me a square integrable function, I want to be able to write it as a linear combination of these kinds of things. And we've seen how to do that already back in chapter 2. We said, given any perfectly square integrable psi of x0, we can write it. Now we have a continuum of these eigenfunctions. We should be able to write it as some function of p, those are my coefficients, times e to the I px over h bar dp. I'm summing over all the p values with coefficients in front of those eigenvalues. And that's sort of like a Fourier transform kind of thing, right? Or inverse Fourier transform, I guess, in this case. Okay. Let me say, there's only 1 minute left, so let me, okay. So in that case, they're going to be real. I think I already said this. Yeah, okay. So this is a repeat of what I just said. We're going to throw away the fact that all of these can be complex numbers and say, we're only going to consider it an eigenvector if it's in our rigged Hilbert space. That means our eigenvalues have to be real, okay? So just going back to the 3 properties we talked about, reality, orthogonality, and completeness, they actually do follow through if you think it through in terms of the rigged Hilbert space. We can now say the eigenvalues of a Hermitian operator are real, even if they have it has a continuous spectrum. You have to think back to what that means. We sort of expanded our space to include just those ones where the eigenvalues ended up being real. Property 2 was about eigenvectors with different eigenvalues being orthogonal. And this we can actually check. Let's take the inner product of these two. Now we're going to get something that is nominally a divergent integral. Okay, so I'm going to take the inner product between the state of definite momentum p and the state of definite momentum p prime, take their inner product, right? I got to put the star on one side. And you get an integral that looks like the integral from -infinity to infinity of e to the I p minus p prime x over h bar. And the question is, well, it is, if you're in calculus, that's a divergent integral. There's no sense to be made of it. But we made an argument back a while ago based on some, it's sort of creative thinking. And there is a way to make this rigorously justified, that when you take this inner product between these two functions, you get a delta function. Okay, the delta function's over here. Delta of k minus k prime can be written this. Now, formally, this is a divergent integral, so you have to kind of know what the integral means, but that can be written as a delta function. And notice, if this is something that is 0, if k is not equal to k prime. K is not equal to k prime, the left-hand side is 0. And it's the same way with this function up here. If we work it out, we can write it, and I'm not going to go into the details here because we're out of time. This integral is proportional to delta of p minus p prime. And that means if p is not equal to p prime, we're talking about eigenfunctions corresponding to distinct eigenvalues, it's equal to 0, because the delta function is only non-zero when p is equal to p prime. So that's property 2. Eigenfunctions corresponding to distinct eigenvalues are orthogonal. Okay, let's stop there. We're almost to the point where we can put all of this stuff together and, just summarize it in like one PowerPoint slide. But the argument is really complicated. Once we get to that point, you'll sort of say, well, there's a discrete case and there's a continuous case. The continuous case is confusing, but we'll sort of hold our breath and take some of the things for granted that it works the same way as it does in this momentum operator case. All right, if anybody wants to stay and talk about stuff briefly, let me know. Just as a reminder, that MATLAB stuff is supposed to be due tomorrow, and I have received a couple of submissions for that already. But come and ask questions if you're still having vexing kinds of problems with your code, or bring it up.